In this video, we're going to take a look here at example 4. We're still going to be working with the disk method, but we're going to see here that on example 4, something strange can sometimes happen when trying to perform this method. Take a look here. I want to find the volume of the solid obtained by rotating this region, which is bounded by these different curves, about the x-axis. So as we've done in the past several problems, I'm going to start by going ahead and drawing out a picture of the region that is being bounded here. Now I'll see that my first curve is y equals 3x, and I'm just trying to get a rough sketch here. So I know that a line with slope 3, I don't know, maybe say it looks something like this. This is my y equals 3x. I'll notice that my other curve is going to have a negative slope. And I can see that if I plug in the value of 4, it's going to end up crossing or hitting a y value of 0, meaning that's going to cross the x-axis. Now, if I was to go ahead and draw a line like this, I could see then that this would be, let's say this crosses my y-axis up here at the value of 12, and then if my y equals 0 is going to be my bottom side, I can see that the total region that I'm working with could be given by this. And so all of my different curves here are accounted for, and I've done a really quick sketch, loose sketch of what my region looks like. Now I just have to figure out what it would look like if I was to rotate this region around the x-axis. So to do that, I'll go over here, and again, I'll sketch out a region similar to the one that I have, but I'll leave this extra space down here at the bottom for my mirror image. I'm just going to go ahead and just draw this triangular space, and again, my duplicate existing down here. And again, I'll just start to play a little game of connect the dots. So I'm going to take a dot that's up here, and its mirror image down there, and pull a line out of the page, back into the page. I'll do the same thing just a couple more times here. So I can see that I have some sort of a figure that looks like this. So this is my 3D solid, and again I can see those circular cross sections being set up here. Now you might be able to guess if this is going to be able to be done as a dx question or as a dy question. But the way that you would spot that is again by noting which way these circles stack. So I'll say, since the disks stack horizontally, we will set up an integral with respect to x. That's what I would need. So I'm going to go ahead and start to measure out the radii of my different circles to see what's going to be happening here. Now, as I do this, notice again, I'm drawing my radii back to the original functions. I'm not going to draw those radii going down because my original functions and original region were not here. I want to draw up into my original region. Now, again, my radii have different lengths, and so I want to figure out how long each of them actually are. So I'll have to come up with a formula for those. However, I'm going to notice something strange, and maybe you can even notice it here as we work through this. How would I actually come up with a formula for the length of those radii? So like if I take a look at my first radius over here, the top side is determined by this 3x function. The bottom side is determined by, well, y-coordinate 0. Notice I get the same exact thing over here for this middle radius, but can I use the formula 3x minus 0 to tell the length of this radius over here? I can see that I definitely can't, because over here I have a new function that's determining the radius for this circle and other circles that are near it. In fact, it almost seems like at exactly this point right here, which would be this point over in the region on the left side, there seems to be a split between the radii for these circles. Now, finding this intersection point is going to be really important for us. I might actually need to know when is it that I switch from having my 3x function on top to my 12 minus 3x function on top. So I'll state here, we find the point of intersection for our curves, but this should be pretty easy. I need 3x to be equal to 12 minus 3x. That means that 12 has got to be equal to 6x, and so x has got to be equal to 2. So over here I have x coordinate 2, and of course if I was to go ahead and plug 2 into either of these functions, I get the value 6 back. So that's the point 2 comma 6. And so I can now see that if I'm on the left side of 2, my radii are determined using the 3x function, but if I'm on the right side of 2, then my radii are determined using this other function. Because of this, I'm going to actually need two different integrals to set up the volume. I'll have a first integral that goes from 0 to 2. And again, I'm going to have pi r squared dx. I'm going to have another integral that's going to tackle the circles that exist from 2 over to 4. That's again going to have a pi r squared dx. So I'm going to go ahead here and start to actually fill in what the radii are. We've already said repeatedly that the radius for those first circles over here on the left is just going to be 3x minus 0. You don't have to write the minus 0. I just like to keep in mind I'm doing like a top minus bottom. And I'm doing the same thing over here, except now I'm going to have a 12 minus 3x minus 0. So here we go. These two integrals represent the grand total volume for the solid. So it's important that I keep in mind that I might need to actually use multiple integrals to tackle some of these questions, depending on if my measurements for different important pieces of my cross-section change over the course of the interval where these sections exist. So again, I'm not going to go ahead and compute this integral here. I'll leave it for you to go ahead and confirm that you can arrive at an answer of 48 pi.